Good afternoon. So today I have, you may have seen the announcement, I had to cancel office hours. I had an opportunity to get an emergency appointment with my dentist, but I got to get here to there. It's about a 30-minute drive from here, so we're going to get through this section by 3 o'clock. So if I can have just kind of focused attention, and it's good because actually we covered most of this already. I've already talked with one student and came to the conclusion that since I canceled office hours today, I should probably have some office hours on Friday. So I'll do that. Looks like it's starting to be fall break or something, so maybe there won't be as many people. Some people might be traveling, that's fine. But Friday, we sort of start to get into the applications of what we're going to do today. So today is a very skills-based derivative thing that really gives us some valuable tools. And then the next two sections will apply those, and then we'll have another test, okay, after some review and such. So let's go ahead. Derivatives of exponential and logarithms. And we are Wednesday, so we're in this section here. Let's back up. So 3.3, and then we've got two more sections. But we've got a little bit with fall break in there. We won't be meeting on Monday. A couple days for review before we go over the test or take the test. So we're in good shape, I think. So let's first look at logarithms. Now you can go into the textbook does have a proof that will walk you through it. But I'm going to do it, I'm going to proof from taking a look at a function f of x. And let's go start with the natural log. So that's what the graph of the natural log looks like. Let's maybe go out a little bit. And I'm just going to let Desmos tell me what the derivative graph looks like. And so you can always have Desmos find the graph of a derivative by this little d dx. What I do is I just put f of x. Okay, so as I change, I can go back up there and change that function up there. Does anyone have an inkling of what that derivative, the blue line, what it kind of looks like? What kind of a function? It's certainly not a logarithm, is it? A logarithm goes like that. Looks like 1 over x. Let's test it. So that's what's, is it y equals 1 over x? Sort of. On the right side, right? But 1 over x has this part down here. But certainly as we zoom in, if we turn the green on and off, it seems to just cover over that part of the blue. But only when x is greater than 0. So but remember, we can always fix this. If I got the syntax right, we can put x greater than 0. I think that does it. Oops. Greater than. And then now it is exactly 1 over x. So on the domain that the logarithm has, remember the logarithms, you can't put negative numbers into them, you can't put zeros. So on the domain of the logarithm, yes, it is 1 over x. Good call. And that's all there is to it. I mean, this is my proof. It's right there. Okay. So again, you can look at how they come up with it. It's like a whole page of things using limits. And we know if they use limits, that's how we came up with the derivatives in the first place. But let's see, what if we didn't have the natural log? Let's put in here, and Desmos will allow you to do like a log-based something else. So we go to functions, we scroll down a bit, and we can actually put in log with some other base. We could do the common log, but let's do log base. Any suggestions? 6? Did I hear 6? I don't know. 6? We'll put 6. Log base 6. Now, does that look like its derivative is 1 over x? Well, if we zoom in on this, we don't have to zoom too far, the blue and the green don't match anymore. Remember, the blue is the derivative. That's what we're trying to match. It doesn't match 1 over x. But it will if we do sort of an adjustment. What do you think that adjustment might be? Well, since the derivative of log is 1 over x, the adjustment should probably be down there. And it's really just going to be the natural log of the base. Because as the base changes, we get slightly different logarithms. So, the shape of the graph of those logarithms change, so their derivatives would change. So they're not going to exactly match 1 over x, but if we adjust them by putting in the natural log of the base, whoa, now we match up. That's my way of proof. Seeing is believing, okay? Now they match up. So this is the derivative. We'll formalize it with it, but you're just going to kind of remember it. Going through the limit proof of it doesn't really help you understand why any more than looking at the graph and saying, this one actually helps you. It is because it is. It's one of my brother's favorite lines. I never thought I'd use it, but I guess it works here, right? It is because it is. Works because it works. Okay. So that's it. That's all we really need to know about logarithms. So let's go back to our story. And we'll click here. And we'll just define it that the log of any base is 1 over x, the natural log of the base. Now, that's actually all you have to remember, because if you think about it, a natural log, if you take the natural log of e, what do you get? You get 1. So then that part will just sort of disappear. But you could kind of think it's there. So we do have another special one that the natural log is so special we have it separate. It doesn't need another natural log of the base because it could become 1. But it's sort of there. Just like we actually are always doing the chain rule, but when it's only x, the chain rule says that derivative of x is 1, so we don't really write it. We don't even talk about it, but we're really doing it. So we're always doing the chain rule. We always have this natural log of the base, but just whenever we do with the natural, we don't have to write it down because it's 1. Okay? So that's all you really need to know about logarithms. The cool part is we're going to look at an application where this will actually help us take the derivatives of some kind of complicated functions. Okay? So that doesn't look very fun to take a derivative of, does it? But because we've got a logarithm, what do we have? We have 3 properties, right? So what we're going to do is we're going to apply log properties, which is going to actually expand this out and actually simplify it, because the same rules that if you have this plus that, you can take the derivatives individually. So this is where we're actually going to say, hey, logarithms are actually a pretty good friend. So first of all, what is a square root? When we have a square root on a logarithm, how do we want to think of that? So what? Raised to the 1/2 power. So we want to see that as an exponent. So we rewrite this as, well, get my pen back. So we're going to rewrite it as the natural log for x minus 6, 9x plus 9, raised to the 1/2. And then what's our first property we can apply to simplify this thing? Not derivative, was not calculus yet. Logarithm rules. The exponent becomes multiplication in front. So we're going to actually expand this out until it becomes easier. Because otherwise, we could use the chain rule. That's not, we could, and then we're going to have to use a quotient rule. It's looking ugly. So what we do is we bring the logarithm property, since we've got a logarithm, just bring this down in front. And at the same time, just so I don't have to write a lot of stuff, when we have 2 things divided, what does that make it? They split into 2 logarithms that are subtracted. So let's see how this looks. This is going to become 1/2 times the whole thing, because it applies there, the natural log of 4x minus 6. Ooh, that's looking much nicer. Minus the natural log of 9x plus 9. Now, do you follow that part? Again, no calculus yet, just logarithm properties. Write the exponent down, make division subtraction, and this is why they use logarithms for the slide rule stuff for calculating, because now we're just dealing with subtraction rather than a quotient. And we can take the derivatives, and one of the properties we're applying is that when we multiply by a constant, we can take the derivative of the inside and just then multiply by the 1/2. So we just sort of, okay, 1/2 is just going to tag along for the ride, as I always say, right? We take the derivative of the inside, and here's where the logarithm derivative is really cool. What's the derivative of a logarithm? 1 over whatever inside it. Then we got to use a chain rule, okay? So it's going to just be, the first part will be 1 over 4x minus 6. But using the chain rule, when we take the derivative of the inside, what do we get? 4. And that actually goes in the numerator, because when we're doing it. It doesn't go down with it. That's sort of the one thing to remember. So whenever you take the derivative of a logarithm, whatever's in there goes into the denominator, and then you use a chain rule. Whatever the chain rule gives you goes up in the top. That's it. And then we've got the second part. So we've got a minus. Again, here we had a logarithm. So that's 9x plus 9. And then chain rule, derivative of 9x plus 9 is 9. And that goes in the numerator. And this, I didn't label it, but this is the derivative. We are done. Notice what's cool about a logarithm is when you take its derivative, there is no more logarithm. That is what makes it really so powerful for doing a lot of different types of things. We're going to apply that. I found this on the web. Shh. So, questions? Does it look too good to be true?
So for the inside, for example, the 4 over 4 minus 6 is the derivative over like the inside?
Well, remember, chain rule says we're taking the derivative of the outside function times the derivative of the inside function. So the inside function is 4x minus 6. So really what's happening is, that's hard to, the way I did it. So the derivative of the first part is 1 over 4x minus 6. The derivative of the second part is just 4. So it's times 4. But because it's really 4 over 1, and that's the way to think of it. Good. Because yeah, you're thinking, that's one of the problems, and I did this a lot. I bring it down there, and then I put the derivative down there, because I thought, oh, it went down there, so the derivative has to go down there. No, derivative stays up top, because chain rule says just take that inside and up on the line, put it in there. Good question. Okay, and notice there is no logarithm here. We're done with logarithms. We've got just a rational function, but that's what its derivative would be. Okay, almost there. So what we're going to do now is we're going to, in the homework there's a lot of examples, and there's some simpler examples than what I've shown you here. I tried to take one that was kind of a little more complicated, but you'll see there's other ones, it's just 1 over and you're done. Okay. The other thing we can do with this, there's a part called logarithmic differentiation. Well, this is just using logarithms as a tool to be able to take a derivative in an easier way. And sometimes there's going to be some examples where this is the only way you can take its derivative, and that's when we've got like x raised to the x power. You can't really, this is the only way you'll be able to deal with it. Okay, so there's a few examples in the homework. I'm going to leave those for you to kind of work with, but use logarithmic differentiation. What logarithmic differentiation does is we call f of x y, just to make it easier. We could still call it f of x. And what we're going to do is we leave this side as it is. We're going to take the logarithm, the natural log of both sides of this equation. So before I rewrite it all out, I'm going to come over here. We're going to write the natural log of y. And remember, this is all y equals all this stuff here. And then we're going to take the natural log of this whole stuff here, 4x minus 7x. Seven x minus 3 raised to the 4th times 6x squared plus 8 fourth, or to the, both are to the fourth, okay. So does it look like we're gonna have to do a product rule and then maybe a chain rule inside of the product rule, and if that's what we would have had to do. But what do we do first? Our logarithm property said when we're multiplying two things, we can rewrite it as what? Addition. And then when we've got an exponent, we can bring that down in front. So we're not even going to have to, well, I guess we still have to use a chain rule a bit, but so we're going to use logarithm rules. This becomes the natural log of 7x minus 3 to the fourth plus natural log 6x squared plus 8 to the fourth. We take those exponents down in front. So the 4 comes down, right? This 4 comes down. You could leave them there, but it's just going to make the derivative a little bit easier to deal with. And then now we're ready to use the easy derivative rule for logarithms. So we take the derivative of natural log of y. What's that? It's 1 over y dy dx. Thanks. So it's really, we're using implicit derivatives, right? Because we've still got, we got a y in it. But you want to see that it works out nice. So this is dy dx. On this other side, we take derivatives, and it's all in response, or it's all in regards to x. So natural log of 7x minus 3, and I'll just basically cross these guys out, right, because we moved them to the front, is, oh, you're going too fast for me. So we'll do it step by step. It's 7x over 3, or 7x minus 3 in the denominator, right, because that's what's in the logarithm. But good, you see, chain rule says we're going to get a 7 coming off in the numerator. But then there's that 4 in front here. We could write it down, but so 4 times 7. Is that okay? Do we see that? Anyone not see that? Okay, so the derivative of 7x minus 3 is 7, so that's going to go in the numerator. This 4 is out there, 4 times 7. So now we can catch up. So good job. Okay. 28. And I'll just put a little note. Here's 4 times 7. Okay. That's all there is to it. Almost. And then we take the derivative of the second one because we've got two sums now. A lot easier to take derivatives this way. Again, just sort of go ahead and write the denominator is going to be whatever's in the logarithm. That's its derivative. Remember, if this was some other base than natural log, we'd have a log, but a constant, but most of them we don't have to do that. And then what's the derivative going to be up here? Derivative of 6x squared is going to be 12x, right? So I'm going to write that here, 12x. And then we've got this 4, so 4 times 12x. We're going to have 48x in the numerator. Okay, so that also looks a little bit more like a chain rule thing, right? Because you see, okay, that where that 6x squared came from, there's still an x left. Now we're almost done. All we have to do is solve for dy dx, because that's really what the derivative is. And so we just multiply both sides by y. Put a parentheses here and here. And so dy dx, or the derivative of the function, is equal to this, but that's kind of weird to show a derivative that has both an x and a y. I mean, not too weird, because we've done it before. But what we're able to do, and what they're going to ask you to do, is we know what y is in terms of x, right? This is what y is in terms of x, right? Y equals this. So we can substitute this. Let's do it in red. What we're going to do is we're going to substitute this in for this y down here. Okay. Let me get this guy out of the way. Does that make sense? So our final answer is going to be this thing. Let's see if I got enough room to write it. 7x minus 3 to the fourth So the derivative of f times 6x squared plus 8 to the fourth. So that's y. And then it's times the stuff we took the derivative of, all this stuff here in the parentheses. 28, 7x minus 3 plus 48x over 6x squared plus 8. That's it. Now, if you would have used the product rule and the chain rule with the original functions, your answer would look different, but algebraically it would be the same thing. That's the thing, is what is really simplified? Well, we don't, I mean, I was going to try to do this. Let's prove it. Let's do it the other way. But you do it the other way and it's the same thing, but it's in a different setup. So this just gets you an answer for the derivative, a function for the derivative, in an easier way. Okay. Now this one we could do both ways. There's going to be ones where they ask you to use, they call this logarithmic differentiation, where that's really the only way to do it. And again, it's always x to the x. You can't do it any other way. It doesn't, we don't have any tools except this particular tool. Okay? And it involves taking the derivative, or taking the log of both sides first, then use implicit differentiation, solve for the dy dx, and usually you're also going to be able to solve, you'll get y time, because it always ends up 1 over y, you multiply by y, but the original function was y, so you get that original function back and it all works out. It's less, it's got that logarithm sort of transformation in between that made the actual taking of the derivative a little easier. And it gives us something we could work with. We've got its derivative now, so we can answer any questions we want to about the rate of change of this function. Okay, just kind of save our brain cells for something else. All right, we're almost there. Now it's the easy part. Exponentials, they're even easier than logarithms. Let's go with that. And again, I've shown you this one a little bit before, but we'll expand it a little bit. So we'll start with the function f of x equals, we'll start with the exponential, the natural number e to the x. And let's see what the derivative of this looks like. Y equals d dx of f of x. Let's see. Yeah, it's in blue. Whoa, where'd it go? Oh, there it is. Oh, there it is. So the blue is the derivative, the red is the function. Do you see any difference? Don't. If you were to do the table of values, they have exactly the same y values. So this is a function where its output values are also the rate of change. It's a very unique function. It's the only one I know of in the whole universe that is its own derivative. That the function is also, if you know the function value, you also know its rate of change. It's pretty cool, pretty nice, but a little difficult because when you can't tell the difference between the derivative and it's like it's a twin. It's like cloning almost, but it is. It's that simple. But as we did last time, what if this was not e to the x? What if it was a different base? And let's go with 6 again, so we see now that blue line doesn't follow it. 6 to the x is not its own derivative. But it's kind of close, right? You could kind of see these they're going in the same direction. They're both exponential, but there's an adjusting factor. What do you think that adjusting factor might be? Natural log of 6. Could it be that simple? It was supposed to be that simple. Why didn't that work? Let's see. 6x So maybe is it divided by? Sometimes you shouldn't have, yeah, okay, so divided by natural. That's why I like that. You just picture you can't lie. I knew it worked before when I was at home, but I forgot I divided instead of I multiplied. So here we go. So if we divide by the natural log of 6, it's going to work. Then this, so it's going to be the derivative, which is just 6x over the natural log of 6. Oh, wait. I know why it didn't work. I'm supposed to do that down here. So that's the derivative. The derivative, sorry. This tooth is doing more to my brain than I thought. Is going to be 6 to the x times times the natural log of 6. That's what works. So I was taking the derivative itself, right? Because the blue line is, I turned this one off. The blue line is Desmos taking the derivative. It's not the same as 6x. But to get the derivative of 6x, what is going on, 6x is part of the derivative. It's just that's what you get. You don't subtract 1 from x, or you don't do anything to it. It's just 6x. But then it's times the natural log of 6. Okay? And when you do that, the derivative, that matches the derivative. Sorry about that. I didn't throw anybody off into too much of a deep spin, did I? Okay. So we'll formalize that with the rules. Sometimes you go there first. So if we have a to the x, here it is, its derivative will be a to the x natural log of a. So in that case of 6, its derivative 6x, 6 to the x, its derivative is 6 to the x, natural log of 6. Okay, so it's kind of an adjusting factor. So exponentials themselves are kind of cool functions. They're pretty close to being their own derivatives. E is the one that is sort of that central, it is its own derivative, and everything else just needs a little bit of adjustment to its derivative to get there, or to the function to match its derivative. Okay. And so we've got this special case, e to the x is its own derivative. But I also want you to remember, this last one is bringing out that we've got to use the chain rule, because if the exponent has extra stuff in there, you got to remember that's inside the function, so you have to use the chain rule with it. So we'll look at a couple examples where we do that, and we're going to be all wrapped up for today. So 3 major things. Natural log is 1 over x, its derivative. Know how to use logarithmic differentiation, and again, it's just take the log of both sides. It'll use log properties to make it simpler to work with. Solve it with implicit differentiation, multiply by y, and then replace that y, because we've got that. So it's just it's a feature that makes complicated ones easier to do and impossible ones possible to do. At least they're impossible by any other method that we've come across. In fact, this is the only method that will work with them. So let's take a look, and this will we'll tie both of them in here. So we've got 2 to the x times log base 9 of x, and we want to take its derivative. So what rule do we have to use here, though? Product rule, good, because we do have a multiplication, so we're actually going to do an exponential, and we're going to do a logarithm. So we might come over here and say, oh, the first, I don't know, we'll do n and n prime, m and m prime. So the first function is 2 to the x. Its derivative is 2 to the x natural log of 2. So we that's taking an exponential. That's all there is to it. M is we're going to define to be the logarithm, log base 9 of x. What is its derivative? 1 over x, and then the natural log of 9. And in that case, it's down in there with the derivative. that's where it might be gets a little. So we've got that, and with the product rule, we just put our pieces together, right? It's going to be, I like to start with the derivative of n times m unchanged plus derivative of m times n unchanged. So we just, however we want to do it. So this is going to be 2 to the x, natural log of 2, times log base 9 of x plus derivative of m, which is 1 over. So this one we actually can make it into a fraction. And then in the numerator, we're going to have the original function 2 to the x. That good? Again, it gets you. The derivatives themselves are, again, fairly simple, but sometimes those are harder to deal with because it's different. We're so used to subtracting 1 from the exponent. So if you catch yourself 2 to the x and you're trying to make it 2 to the x minus 1, you're not alone. It's one of the things, oh wait, no, it's different. It's an x up there. Can't do that. We're not subtracting 1 from the exponent. It is its own derivative. Okay? Doing good? Okay, now this one's really hard. Just threw it in here at the bottom. What do we do to get that derivative? Gotcha. Caught myself too. I was going, oh, how are we going to do this? Is there any variable in there? There's no variable. It's a constant. Oh, shoot, what's the derivative of a constant? 0. But, you know, it took me 15 minutes to figure that out. Then I looked at the solution. Oh, yeah, there's no... Because you see, e, you think of a variable, but e is not a variable. E is a number. It's raised to the 6. It's just a number. Its derivative is 0. Log of 5. Natural log of 5. It's a number. It's a constant. Derivative is 0. So this one's actually quite easy, but it's in the homework, so I save you a little bit of time where you don't have to look at it for 15 minutes and try to figure out how to do it. And then finally just say, oh, it's a constant, right? And then I checked it. At least I figured it out first, and then I checked the solution. Yeah, it's a constant. Okay? I think this will be our last one. This one is with the chain rule. So it's e, so it's got the natural base. So it's going to be one of the easy ones. It doesn't have a modifier. So we'll get its derivative. Again, first step is the derivative. It is itself. E to the square root of 3x plus 2. Nothing to do. It's just such, it is its own derivative, even there. The only thing we have to do now is we have to, and I'll emphasize it, we have to get the derivative of the exponent, 3x plus 2, right? We got to take that derivative. And so then we see this is a square root, so that's a 1/2 power. I'll just kind of do my work this way. So we're going to take its derivative, and so there's actually a chain rule within a chain rule here, right? Because we have to take the outside function is going to be 1/2. And notice this is down on the main line. This is not up in the exponent anymore. This is 1/2, 3x plus 2, all unchanged. Subtract 1 from the exponent on this one. So we're going to get a negative 1/2. And then we've got to multiply by the derivative of the inside, which is 3, right? 3x, derivative of 3x is 3. Derivative of 2 is 0. So we've got this. And then, again, this little guy just kind of follows along. I'm going to write it down here so I don't have to rewrite it too many times. And then I'm going to clean this up a little bit. So we've got 3 times 1/2. That's going to be 3 halves. I'm going to move this down into the denominator. Oh, wait. So we're going to get, if I rewrite this, we're going to multiply this, right? 3 times this. So I'm going to move it up that there. The 2 is in the denominator, and this is a negative 1/2, so that's a square root of 3x plus 2 in the denominator. And again, you could write them side by side if you wanted to with a negative exponent, or, you know, but that's kind of what you start seeing. But you always see when you have an e to the power, it's always going to be there. If there's more stuff, it's because of the chain rule. So, and again, it feels like some magic's going on or something, because it doesn't feel like we're doing anything, but it's just because it is its own derivative. Its own derivative. So, there's 28 problems. Again, it sounds like a lot, but some of them are pretty, like that one, it's 0. So, and then there's some other more simple ones. I tried to get the ones that were a little bit more complicated. Get some practice. Remember, I've got office hours Friday. If you want, we'll hang out and do as many problems as you want.